Good morning, everyone. Once again, welcome you back for the session 43 and 44. In this session, we are going to deal about the Z transform. What we mean by Z transform, we are going to discuss here. Before, let me introduce this Z transform. As we know that in this semester or in this year, you come across three types of transformation. One is a Laplace transform, another one is Fourier transform, and this is the Z transform. I think we have all know that what we mean by Fourier transform and Z transform. Assuming that you are knowing the things, once again I will just tell when we are going to apply this Fourier transform, when we are going to apply Laplace transform, and this whatever we say, this is a transform. As we know that Fourier transform is applied for continuous function. When Fourier transform is failed, then we think of Laplace transform. Laplace transform is also applied on continuous function. Now the question comes that when we are going to use this Z transform is applied for discrete function. What we mean by discrete function means you won't get the continuity there. There will be a gap between. So you just if you want to assume, you can assume the staircase. What is the staircase? There is a pole between one some distance, right? It following some big one, big one, big one, big one, right? In that manner, small to bigger in length, there is a gap between the two poles, right? Where I'm talking about staircase. Whereas if you see the continuous function, if you imagine that the sine function, that is nothing but an continuous function, right? So Z transform is applied for a discrete function, and that too it is an on the infinite summation it is, right? So let me try to introduce this Z transform. Z transform operates on the sequence of a function of single variable defined for non-negative integral. Please remember these words: operate on sequence of function of single variable defined for non-negative integral values of the variable. This transformation finds many application, as I said in Laplace transform. Here also many applications you will get. This is what the introduction and definition. Definition says if un is equal to fn, even you might knowing in previous year we are using un for the summations and sequences. When you done comparison test, you have done alternating series test, Cauchy's, you have done many tests to see the convergency. So un is equal to fn defined for all positive numbers. See what numbers are there: 0, 1, 2, dot dot up to whatever the known number, and even will become 0 when n is less than 0. What it means, we cannot, if negative values occur, that one will get as 0, mean to say even will get as 0. Then this is the condition. What is that? It is defined for positive integer. When you take the negative integer, it will get as 0. That function you are selecting. Then Z transform on even now, denoted by ZTUN, is defined by, this is the way you are going to get. Z transform of un is equal to summation n running from 0 to infinity un z to the power minus n. Now you just observe the RHS. When I can say it is convergent means when I supply some values of this n, and I will check whether the answer is known to me or not. If it is known, then I can say Z transform is exist and it is convergent, right? So the RHS is converges, it will be a function of Z. Mean to say that when we get the answer, we will get in terms of Z only instead of UN. UN will vanish, whatever the answers you will get, that is in terms of Z only you will get. Therefore, we are telling it will be function of Z and we can write. Here you see the RHS part, that is U bar of Z. U bar of Z is nothing but the answer after substituting the n values in the summation. The above expression can be equivalently expressed as inverse Z transform of U bar of Z is equal to UN. Right. This is called inverse Laplace transform. This is what the definition of Laplace transform. Now let me find some Z transform. Before going to the actual problem, one property I want to do. Z transform of n to the power k. We have to show this answer as minus z d by dz z transform of n to the power k minus 1, where k is positive integer. To have this, what I have to do, we have to consider once again the definition of Z transform. As you know, that definition of un is equal to what? Summation n running from 0 to infinity un z to the power minus n is there. So according to the definition, I am writing this one as, yeah, here you see in the place of un we took n to the power k. So summation n run from 0 to infinity n to the power k z to the power minus n. Now without disturbing which one is a variable here, variable will become as here n. So z over what I am doing is I want to get the answer. So what I am doing is that I am multiplying the z and dividing by z and keeping whatever n to the power k z to the power minus n as it is. What extra thing I am doing is that I am multiplying with z and dividing by z. So once again the same answer you will get. So I made here equals to z summation n run from 0 to infinity 1 by z z to the power k z to the power n. Right. The same thing I wrote here. Okay, what next step I will do is that whatever the denominator n is there inside the summation, I will adjust that one. Outside z as it is. I am not disturbing the outside z, outside the summation. I am writing as it is. Z summation n run from 0 to infinity n to the power k z to the power minus n plus 1. Where this extra 1 has came? Because I have multiplied and divided by 1 by z. 1 by z is taken into the account. Therefore, z to the power minus n n plus 1 it is. Now you can see this one, what I am doing here. Here what it is, outside z it is summation n run from 0 to infinity. I am going to make some manipulation in terms of n. So what I am making is that I am multiplying n and dividing by n. So multiplication I wrote as n to the power k is already there, minus 1. Why minus 1? I said multiplying and dividing by n, therefore you will get k n to the power k minus 1. This one as it is, z to the power minus of n plus 1. Right. Let me say this as equation 1. Once again by the definition, if I want to write z transform of n to the power k minus 1 is equal to summation n runs from 0 to infinity k to the power k minus 1 z to the power minus n it is. This is what the same thing I have done here. Now what I will do is that, as in that proof we needed the differentiation, therefore I want to do differentiation with respect to z. So if you do the differentiation with respect to z, we will get d by dz, z transform of n to the power k minus 1 is equal to in summation n runs from 0 to infinity n to the power k minus 1. You are doing with respect to z, so what you will get? Minus n z to the power n minus 1 minus n minus 1, right? Z to the power minus n minus 1. So what I will do is that this whatever the RHS part minus is there, I took to the left hand side. So I made this equation look like, so n to the power k minus 1 into n z to the power minus I took as in common, then it will become n plus 1. Now what I will do is that I got equation 1 and 2. I want to use the equation 1 in 2. So how it looks? This is the equation 1 and this is the equation 2. Whatever the summation is there, you just see in equation 1, z summation n, I am talking about only equation 1, z summation n runs from 0 to infinity n to the power k minus 1, z to the power minus n plus 1 dot dot 1 is there. In place of this summation, I will put this one RHS equation 2. You just see everything is same, only z is missing. So I will rewrite this equation. Okay, what is that equation? Now you just see equation 1. Equation 1 means LHS is as it is, z transform of n to the power k is equal to minus whatever is there, RHS is replaced by LHS of equation 2. I am repeating, RHS of equation 1 is replaced by LHS of equation 2. So after replacing, we will get the required answer. This is the required answer of the thing. Now let me go some standard examples of this z transform. Z to the power z transform of n to the power k. By the definition, what you will write? By the definition, you will write in the place of un, you are replacing k to the power n, z to the power minus n. So this is equal to summation n run from 0 to infinity k by z whole to the power n is there, right? Now if you substitute the values of n over here, first n value will be 0, so something raised to 0 is 1. Second time it will get as 1, so you will get k by z. So third time it will get as k by z whole to the power 2 and so on. See here, this is nothing but one series you will get. What is that series? This is called an geometric series. We know how to get the sum of this. Sum to infinity is given by 1 minus r. Here r in the sense what it is, k by z. Let me put all these things. Yeah, you just see 1 by 1 minus k by z. Now take the LCM and simplify. You will get z by z minus k. This is the first answer. Now let me go for the z transform of 1. So what is that z transform of 1 here? Now by using the formula, put k to the power n is equal to 1 in previous formula. So what you will get? Wherever k to the power n is there, I am going to put as 1. So it looks like z by z minus 1. Now z transform of n here. Yeah. We are using the property of this, what is that, just now we have done before coming to the examples. This is the theorem result. What it says is that z transform of n to the power k is equal to minus z d by dz z transform of n to the power k minus 1, right? Now put k is equal to 1. So when you put k is equal to 1, what will happen? we will get a Z transform of n. Z transform of n, and you put in this formula, above formula what I said, Z transform of n to the power k is equal to minus 1 z d by dz, Z transform of n to the power k minus 1, you said, right? Now what I am doing is that I am taking k value as 1 in the formula. So when you put it that 1, you will get Z transform of n is equal to minus z d by dz, Z transform of 1. You know already Z transform of 1. What is that? Z divided by Z minus 1. You just put and to do the differentiation. Yeah. So if you do the differentiation of this, what you will get? Yeah. Z minus 1, Z differentiation will be 1 minus Z, right? Minus Z, Z minus 1 whole to the power 2. So after doing the simplification, we will get the Z transform of n as Z by Z minus 1 whole to the power 2, right? Now Z transform of n square. What is that Z transform of n square here? Once again, using the same formula what we are using the property. What is that property? Yeah, this is the property we are using. Z transform of n to the power k is equal to minus z d by dz, Z transform of n to the power k minus 1. Now n value I am k value I am taking as 2 here now. K value is 2. And put in above equation. What will get then? Z transform of n square is equal to minus z d by dz, Z transform of n. N just now you have found out. You are placing k value as 2. So n to the power k value will be 2. 2 minus 1, it will be 1. So Z transform of n. Z transform of n you know. I am supplying that Z transform of n as Z by Z minus 1 whole square. So when you apply this one, right, this is the step repeated. Now when you do the differentiation quotient rule, what the quotient rule says? The denominator part you will keep as it is. What is denominator part here? Z minus 1 whole to the power 2. Differentiation of Z will be 1. Minus numerator as it is, Z as it is. So differentiation of denominator, that will be 2 Z minus 1 divided by Z minus 1 whole to the power 4. What is the common thing we will observe here? The common thing is Z to the power minus 1 will be the common thing is there, and after simplifying this, we obtained minus Z minus 1. So if you replace that one, you will get the final answer as Z square plus Z, Z minus 1 whole to the power 3. This is the basic things you have to remember. Now Z transform of cube, once again the same procedure I am doing here. What is the same procedure in the sense here? Z transform of this is a property I am using here. Yeah, now k is equal to 3 in this formula we will obtain. Okay, now Z transform of n square can be written as in this form. Okay, so you just try to obtain the differentiation. Okay, differentiation a little bit big is there here. Yeah, you can take a look of it. Differentiation I'm talking about this one. Here what it is, denominator part is Z minus 1 whole to the power 3 and numerator part is Z square plus 1 is there. So Z minus 1 whole to the power 3 first time, and differentiation of that will be 2Z plus 1 minus Z square plus Z 3 into Z minus 1 whole square. What is the common thing you will see? Z minus 1 whole to the power 2 is the common thing. Okay, now you simplify this. Take your time and simplify. When you simplify, we will get in this form. Okay, Z transform finally we obtained in this one, and thank you for the patient's hearing.